Hello and welcome to Database Management Systems. I'm Jovita Christie, and in this video, I'm going to explain to you schedules in transaction management. So let's begin. First of all, we'll see what schedules are, and we'll see an example of a schedule. So consider this transaction. This transaction is a transaction T1, and here you can see there are two variables, A and B. And what this transaction does is it reads the value of A and then subtracts 50 from it and writes the same value back. And then it reads the value of B and adds 50 to it and writes it back. So this is a very simple T1 schedule, and I've used this in the previous videos also. So you can think of a scenario where A and B are accounts, and so this transaction is actually transferring the amount of 50 from A to B, because from A it is being subtracted and it is being added into B. So this is one transaction. Now I have another transaction, which is transaction T2. And in transaction T2, what is happening is there's a 10% deduction from A, which is then added to B. So if you look at the transaction, you can see that T2 is first of all reading A, and then it is taking a temp variable where it is storing 0.1 times A, which means it is storing 10% of the amount in A in a variable temp. And then this temp variable is subtracted from A, but it is also added into B. So once again, T1 is transferring 50 from A to B, and T2 is transferring 10% of A from A to B. So these are two transactions. Now, if both transactions have to take place or execute simultaneously in my system, then I need to provide a schedule for them, which is almost like a timetable, where I can tell which instruction, which operation will happen first and which operation will happen next. So that is how you can create a schedule. So in transaction T1, these are all the operations available. And what will happen here is these operations will be executed one by one. But from here, the operations that I need, the operations that are most important are the read and write operations, because those are the only operations where the memory is being used. In other operations, the memory is not being used. It's just a calculation. And so we'll only extract the read and write operations from T1. So what you can see here is read and write operations of T1 extracted from T1. And now let's bring back T2, and we'll do the same with this one. We will extract the read and write operations. So what you can see here is the T2 transaction with read and write extracted. So what we get now are two transactions, T1 and T2, with only their read and write operations available. Everything else, which was the calculation part, is removed. Now we can arrange these into a schedule, into a timetable. So there are several ways of doing that. One such way is simply creating a schedule in this manner. So what you see here is there is a transaction T1 and transaction T2, and T1 is first going to perform read A and write A, both operations. And then after that, T2 will perform read A and write A. Then again, T1 is performing read B, write B. And then once again, it is T2's turn to do read B and write B. So this is what a schedule looks like. And before I proceed further, let us now define a schedule. So schedule is nothing but a chronological order in which instructions are executed in the system. So a chronological order is basically an order where you specify what is first, what is second, what is third. And that's what we have done here. So you can see in this schedule that both the transactions are happening simultaneously. And that's why this is known as a concurrent schedule, But there is also a way of having a serial schedule. A serial schedule is a schedule where one transaction happens, and once it's over, then the second transaction happens. So let's take a look at it. This is one serial schedule where the transaction T1 happens first, and once it is fully finished, only then transaction T2 starts and does its work. So you can also have another variant of this where transaction T2 happens first and then transaction T1 happens. So this way you can have serial schedules where one transaction takes place after another transaction. Obviously, concurrency has its own benefits, because imagine if you were actually using such a banking system where only after one transaction is over, you can perform another transaction. Then you would have to wait for somebody to finish their transaction in order to do your own transaction. So this serial schedule is possible, but this is not what is done in practice. In practice, we use concurrent schedules that we saw earlier. Now let me define what a serial schedule is. So a serial schedule consists of a sequence of instructions from various transactions where the instructions belonging to one single transaction appear together in that schedule. So whenever you have sequence of instructions of one transaction appearing together in one schedule, then it is known as a serial schedule. So all instructions are appearing at the same time together, then it is a serial schedule. Now, what we're going to study after this are isolation levels. So isolation and concurrency are opposites of each other, but in any system, you get to decide how much isolation and how much concurrency you wish to have. So we are going to see different levels of isolation. So when we say level 1, then level 1 would be the highest amount of isolation and least amount of concurrency. And there are 4 levels, so the 4th level would have least amount of isolation and maximum amount of concurrency. And isolation is also one of the ACID properties that we studied in the first video on transaction management. So the first isolation level is known as serializable level. So a serializable level is where all schedules are totally serial schedules, where one transaction takes place after another transaction. The second isolation level is known as the repeatable read level. Here, only committed data is allowed to be read, which means if there's a transaction that has written a data item A, then another transaction can read that data item A only after that previous transaction has committed. So once again, if there are two transactions, T1 and T2, and T1 has written a data item A, then T2 can read that data item only after T1 commits. And there's also one additional condition here, which is that between two reads of a data item by a transaction, no other transaction is allowed to update it. So if I have transaction T1 and it is reading a data item A twice, then between that period where it reads data item A the first time and the second time, in that period, no other transaction should be able to update that data item, so that when T1 reads the data item, both the times it gets the same value unless T1 itself changed anything in that data item A. So this is known as repeatable read isolation level, which has slightly less isolation than serializable level and more concurrency than the serializable level. The next level is known as read committed. Read committed level is very much like the updatable read level that we saw just now, but only difference is that updatable read, repeatable read, condition is removed. So you can see here that all committed data can be read, but you do not require repeatable reads, which means between two reads of a data item, another transaction can change the data item. So once again, as we proceed, the isolation decreases and concurrency increases. And so our fourth level is where there is maximum concurrency and very little isolation. So it is also the lowest isolation level which is allowed by SQL. And it is known as read uncommitted. This allows uncommitted data to be read. Uncommitted data is where if I have a transaction T1 and the transaction T1 is reading a data item A, then that transaction, even if it does not commit, another transaction T2 can still read the data item A. So that is known as read uncommitted. And those are the four isolation levels that we have in SQL or in DBMS in general. Now we're going to see two more types of schedules. We've already seen serial schedules and concurrent schedules. Now we are going to see recoverable schedules and non-recoverable schedules, which are opposite of each other. And we are also going to see cascading schedules and cascadeless schedules. So let's take a look at recoverable schedules. And in this, I'm going to begin with, first of all, the definition. So a recoverable schedule is one where for each pair of transactions, Ti and Tj, such that Tj reads a data item previously written by Ti, the commit operation of Ti appears before the commit operation of Tj. So whichever transaction is writing the data item, and whichever transaction, so there are two transactions writing, one is writing, another one is reading the same thing written by that transaction. So the transaction that wrote the data item must commit first, and then the second transaction. And the reason for this you'll come to know in a little bit. So you can see here, this is an example schedule. In this, this is not a complete schedule because there are two transactions, T6 and T7, out of which T6 hasn't committed yet. So it is only a partial schedule, and for our example purpose, partial schedule is okay. So there are two transactions, T6 and T7. T6 is performing read A and then write A, which means it has read the value of A and it made some calculations, and now it is writing A back to the memory. Now what happens here is T2 is reading A. So when T2 is reading A, it is going to get the value that is written by T6. So the value read by T7 is the value actually written by T6. But T7 is already committing. As soon as T7 has finished reading, it is committing. So in this case, you might not see a problem right now, but suppose T6 gets aborted going forward. Because of some errors, T6 is not able to commit and it gets aborted. And if you watched the video on states of a transaction, then after the transaction is aborted, there are only two things you can do. One is to roll back the transaction, and that means to restart it. And another thing you can do is to kill it. In either cases, whatever changes the transaction has made into the system have to be removed. So that means T6 had written some value of A, and that value has to be changed back to its original, whatever original value it had. So if A was 50 and T6 made it 100, then if T6 fails, then A has to become 50 once again. Otherwise, there will be some inconsistency in the database. So that is what needs to be done. Now, if A becomes 50 once again, then the value read by T7 is wrong because T7 read the value 100 and performed all calculations based on that value. So T7 would also have to be rolled back, but we cannot roll back a transaction that has already committed. And that's why you see this schedule is a non-recoverable schedule, because in the case of an error, we cannot get our original data back using this schedule. And so that's why this definition is there of recoverable schedule, which says that every transaction, if there are two Ti and Tj, and if Tj is reading something written by Ti, then Ti must commit first, and then Tj should commit. So that if Ti fails, we can always roll back Tj also. Now let's talk about, before I move there, let me just tell you how to make this a recoverable schedule. This is not a recoverable schedule right now, but if you want to make it a recoverable schedule, you will simply have to remove the commit operation of T7. And after removing it, you will put it somewhere, because it's partial, you would put it somewhere afterwards, where after T6 commits. So once T6 finishes everything, then T6 will commit, and only then T7 should commit. Then it becomes a recoverable schedule. Now let's see the second type of schedule, which is cascade-less schedule. So a cascade-less schedule, for that, first you need to understand what is cascading. So let's see this example. Here I have 3 transactions, T8, T9, and T10. In these 3 transactions, once again, only read and write operations are given. And you can see that here T8 is writing the value of A, which is then read by T9. And T9 is also, after reading and performing some calculations, is also writing the value of A, which is then read by T10. Now, up to that, everything is fine, but what happens afterwards is abort. So T8 is aborting. When T8 is aborting, what we need to do is undo all the changes made by T8, which means T8 performed write A, and I need to remove that write A. So it's the same thing as what we saw in recoverable schedules. If T8 made the value of A to be 100 from 50, then we need to make it 50 again. And if we do that, then there's a problem with T9, that T9 also read the new value of A. And so we need to roll back T9 also. And if we roll back T9, then we also need to roll back T10, because T10 also read the value of A written by T9. So you see what's happening here is, because of one transaction being aborted, we have to abort several other transactions that are dependent on each other. This type of a situation is known as a cascading rollback, where because of one transaction, several transactions are rolled back. And this schedule is a cascading schedule. But we would like to make a cascade-less schedule, and I'll tell you how to do that. So to make it a cascade-less schedule, you have to follow these rules. It is the rule for cascade-less schedule, which is for each pair of transactions Ti and Tj, such that Tj reads a data item previously written by Ti. Now up to here, it's almost the same as a recoverable schedule, the definition. After that, the condition is there. The condition says that the commit operation of Ti must appear before the read operation of Tj. So before, in this example, before T9 is reading the data item A, T8 should have committed. Only then you should allow T9 to read the data item A. And if T10 wants to read the data item A, it should read the data item A only after T9 has committed. So that is how you can ensure that your schedule becomes a cascade-less schedule. And it's needless to say that every cascade-less schedule is also a recoverable schedule. So that's what you can know. That's all that there is to know about schedules, and that's it for this video. And I'll see you in the next one. Thank you for watching.